last week about, thank you, about, we talked Friday about stoichiometric calculations, basically going from mass of something to mass of something else. It could be from a mass of a reactant to a mass of another reactant. It could be from a mass of a reactant to a product. I guess the other thing is product to the reactant, or from a product to another product. Just basically, and it's usually grams to grams. Okay? But now kind of related to that is this kind of on the front end of a problem called limited supply stoichiometry. So in a limited supply stoichiometric calculation, it's like a pre-calculation before your ordinary calculation that you guys handed in. It's a check to see what you're going to run out of first, basically. It focuses on the pair of reactant or 3 reactants or 4 reactants, and whatever you're going to run out of first, we call that the limited reactant. Okay, the reactants that's limited reactant or the reactant in limited supply, and that's the most important one. And I'm gonna, here I have a picture of making brownies. I picked it because the brownies look delicious, okay? And it's kind of like if you want to make a bunch of brownies, one of your ingredients probably is out of proportion in a short amount compared to your other ingredients, and that's your limited reactant. Everything else is in excess. So, Friday we did a couple stoichiometric calculations with P4 and Cl2, and we said, was it Cl2 was there in excess or P4 was there in excess? Anyway, the other one was there in excess, and this is why we said that. Okay, this is going to make more sense if we talk about this sort of problem. Okay, so let me show you before I do the ham sandwich thing. Just today I put this together because I always think of it like this instead of the ham sandwich. Where's my picture of my brownie? There it is. All right, there's my brownie. Yum. Oh my gosh. It says a simple recipe. It looks pretty simple. It's like something I could do. Okay, but I want to focus, draw your attention to a few things. The ingredients in addition to the picture. And then the 20 servings is one batch, right? So bottom line, if you go to your cupboard and you find in your cupboard 4 cups of sugar and 3 cups of flour, and you want to make as many batches as possible, how many batches can you make? Here's your sugar, here's your flour. You can make 2, exactly. You make 2 batches, and actually this example, would you have any, if you made 2 batches, would you have any sugar left over? Mm-mm. Any flour left over? Mm-mm. That doesn't happen very often in chemistry. We say, and it does, when we do titrations, actually, that's what we're going to count on. Basically, we used up both ingredients, the exact stoichiometric ratio, okay, to the amount we had. All right, let's say you go to the cupboard another day, you went shopping, and now instead of 4 cups of sugar, you have 6 cups of sugar, but you forgot to buy flour. You only have 3 cups of flour. So how many batches can you make?
2.
Only 2. Exactly. And which one are you going to run out of first?
Flour.
You're going to run out of your flour. Exactly. That's all it is. That's all it is, people. Okay? So your flour was the thing that drove how much you could make, right? And so that was there in limited supply. Are you going to have sugar left over? Yeah. In fact, a type of calculation we're going to be doing is to say how much sugar would you have left over. Okay. So here's where I'm going to end up. Okay, here we go. So you can't go wrong with a ratio. So here's what this looks like. See, the 3 cups of flour was what we have from the recipe. So when you guys balanced your equations, that's like coming up with a recipe. From the recipe, we know for one batch we need to consume 1.5 cups of flour. Okay, so cups of flour cancel, we're left with units of batches, which you guys told me too. That's perfect. So let's go see how much sugar, sugar we'll consume. So in these problems I'm going to show you with chemicals, we have a limited supply reactant, and that's our first term, Okay, we do all of our stoichiometry based on that. So if we want to see how much sugar we're going to consume, we're going to go back to the recipe. The recipe says we have 2 cups of sugar to consume for every 1.5 cup of flour. Okay, that's where that comes from. Units of flour cans, and we're left with units of cups of sugar that we're going to use. You guys would probably tell me 4, and you're right. 4 cups of sugar. So I need to see that. So how much sugar do we have remaining? Well, it's that 6 minus 4, or 2. That's it. That is totally it, in a nutshell, with something more delicious than nitrogen and hydrogen and ammonia. Yes? Did you answer your, yeah. Did you answer your own question? Okay, so back to the ham sandwich problem. It's very similar. Okay, so a lot of times what I'll do is kind of, I already showed you, I kind of write underneath the species. This whole word paragraph thing, I don't do very good with it. So you have 20 slices of bread, so I'll put 20 under my bread, 20 slices. And it says we have 7 slices of ham. And we want to make as many sandwiches as possible. So which one are we going to run out of first?
Ham.
We are going to run out of ham first. How'd you get that?
The ratio.
The ratio. So you figure with ham we could make 7 sandwiches, and with bread we could make 10. In fact, that's one way to come up with what are we going to run out of first, is what can give you more sandwiches. What can give you the fewest amount of sandwiches is your limited reactant. In this case, it's ham. Perfect. Well, let's kind of walk through this problem. I'm going to kind of introduce something that's called the need versus have ratios. I'm kind of a firm believer. There's 3 ways to identify the limited, which one you're going to run out of first. The limited supply reactant. 3 ways. Okay, and you get a pick. I kind of like this need versus have. The need we get from the recipe. The need we get from the balanced chemical equation. So what we need is 2 slices of bread for every 1 slice of ham. Need. That's it. What we have was given in the amounts. And what you do is you go the same units. So what we have is 20 slices of bread per 7 slices of ham. You divide that out, and you got 1.86 slices of bread per 1 slice of ham. Then I usually go get my cup of coffee, and then I come back and I focus on the words need. That was from the equation, and have, that was from the problem. Okay, and so can you see where it looks like I have, oh, I lost my red. I have more, that's greater, than I need. Have what? Need what? Well, I have more bread than I need. I have more bread than I need. Have more bread than I need. So bread must be in excess. Okay, and that's what you guys told me to start out. But this is how we can do it with chemicals. Okay, so you compare the have and the need ratio. Again, the very last, near the last slide, before your assignment slide, I'm going to show you the 2 other ways to go about this. But for me, I'm going to kind of stick with this, come up with a have ratio from your balanced chemical equation, the stoichiometric ratio, compare that with your need from the ratio, and compare that with your have that you're given. All right. So let's finish the other questions. That was just the first question. And it kind of goes wait, limited, which is limited, show me how you get it, and then you do the other calculations, okay? So we're ready to do the other calculations. So we base everything upon ham because that's what we're going to run out of. So now these look kind of silly, but these are ratios from this equation. So we have 7 slices of ham from the relationship given in the equation, for every one sandwich, we need one slice of ham. This is the first question, like how many are this is the second question. After you identify the limited supply, which is ham, how many sandwiches can you make? Well, we can make one sandwich for every one slice of ham. Okay, I can do that math, right? So that means we can make 7 sandwiches. That's it. I think the next question was, of the thing in excess, which is bread, how much is going to be left over? So, oh, yeah. The stuff that's left over, bread is in excess. How much will we use? Well, we have to do another stoichiometric calculation, faux stoichiometric calculation in this case, starting with the thing that was in limited supply that we have. That's 7 slices of ham that we have over 1. And from the relationship in the kind of faux equation, we need 2 slices of bread for every 1 slice of ham. So units of slices of ham cancel. We're left with units of slices of bread, which of course that is 14. 14 slices of bread. And we have one more question to answer, and it will involve subtraction. Because that one more question is, we had 20 slices, we're going to use 14, so how much of the excess reactant or ingredient we're going to have left? And it just simply looks like this. 20 slices of bread minus 14 slices of bread is equal to 6 slices of bread. That's it. It's kind of the set. The stoichiometric calculations are, unlike some other chemistry calculations, pretty standard. They're like, not a lot of variations. Okay. So, but I hope you need to get used to, how do I say this? You need to really get used to that first part. Which reactant are you going to run out of first? Have to be your limited supply reactant. And then do your calculation based upon the one that's limited amount. It's not fair to guess. A 50-50 chance? I don't think so. Okay? So this is I don't know if this is in your textbook or if this is an earlier textbook, but basically over here we have the product, and if you read the caption, it says you need one of these and you need one of these. Bottom line is, how many reports can you make? Well, you automatically know that relative to these two, the instructions is you're going to run out of first. Okay? You need 2 of these. Well, if you take 83 times 2, you get 166. Well, to me, you're still going to run out of that one first. Does that seem right? Okay. And then last but not least, you need 4 of these. And if you take 4 times 83, what you're going to find out is that you are actually going to run out of these the purple is graph paper. You're going to run out of that first. Okay, so it's another type of look at that. Okay, so switching gears. This is sometimes called the Haber process. Is how hydrogen and nitrogen gases in their gaseous state can go to form ammonia, NH3, also in its gaseous state. So we're going to look at that, look at some calculations based upon that. This video is not working, no surprise there. 6 and 12. How are we doing for time? But let me just kind of tell you, so we have 6 molecules, and we have 12 molecules of that. If we could have animated that video, it's almost like my videos have expired. I don't know after 10 years if they die or what. Okay, that's what you have. And so let's just kind of, for kicks, walk through how I like to do these things. I come up with what I call a need ratio and a have ratio. Now, I like larger numbers that are larger than 1. So I usually pick the one that's greater. So the need ratio comes from the balanced equation. So do you see that we need 3 moles of H2 for every, what, 1 mole of N2? I can do that math. Okay, so that means that we have a ratio of 3 moles H2 to N2. That's what we need. And then what you do is you do the same units. Okay, so we're going to go H2 over N2 for a halve ratio. Bless you. Bless you. So of course my halve is going to focus on the 6 molecules and 12 molecules, but I'm going to go H2 in the top. So what I have is 12 molecules of H2 for every 6 molecules, I can do that math too, of N2. I divide it out and it's looking like 2. So what I have is 2 molecules. I can just go ahead and scale molecules up to moles if that's okay with you. I have 2 moles of H2 for every mole of N2. So can you see with regard to the H2 that I need more than I have? Does that make sense? That's the H2. So that makes H2 limited. That's what I'm liking. Okay. So that's how that works. All right. So, oops, okay. So just like I've been saying, it goes back to the brownies. Okay, you guys told me I was going to run out of flour first. So that drove, the flour drove how many batches I could make when I went to my cupboard and I had my second time. And it also drove how much sugar I was going to use. So the one that's in limited supply is what you do your follow-up calculations on. Now, on your unit exam, I will have, on your Unit 2 exam, which is the 20th, okay, it's the 20th of this month finally, I will have a problem just where I want you to identify which is in limited supply, and I will have probably an assortment of ordinary stoichiometric calculations. Okay. All right, so let's do it again. But instead of like molecules, we're going to have, this is more normal, we're going to have some masses here. So like I said, and I don't know whether I kind of tease like I'm buying time or whatever, but I like to draw the numbers out and put them with the species if I already have an equation up there. So what I'm saying is I like to take my 72 grams of N2 and I put it under my N2. Why not? And then I like to take my 22.0 grams of H2 and put it under my H2. Okay, it's just less likely to confuse what's what. All right, so right off the bat, this is the one that we just learned today. Which one are you going to run out of first? Now, right away, do you see our first step? Does this make sense to you? Our first step is to go to moles. We got to go to moles. And we've been talking about how you do that. It's just the molar mass. And then finally, once we have them in moles, you're going to see me go ahead and take my need ratio from the coefficients of the balanced equation, and then my halve ratio from these masses that were converted to moles, and then compare them. That's it. So that's the first step. All of that stuff in the first step. It's like weird, right? But it's an important calculation in chemistry. After that, 2 and 3, those are just what you kind of like what you guys handed in. 2 is what is the mass of the excess reactant that will be remaining? Well, we're going to find how much is going to be consumed, ordinary stoichiometric calculation, and then we're going to do a subtraction. And then 3, bada boom, is just given the mass of your limited reactant, how much product will be produced. That's it. So it's kind of the first step that's something new today. All right, so do you guys have these molar masses? Yep, you do. Molar masses of everything. So I gotta see these, and I get to be kind of a jerk about it. So like on your unit exam, if you get everything right and you don't show me these calculations, nope, you won't get 100% of points.
So to find the molar mass of the molecules, since there's 2 of the nitrogen, do you take the molar mass times 2?
Okay, so is this what you mean, this subscript 2? We took it times the molar mass, we took the molar mass of 1 nitrogen times 2.
Yeah, that's what I'm saying, since there's 2 over there, that's it, okay.
Yep, yep. But one of the things, and as far as I can tell, I haven't graded your stuff yet, but sometimes students, I'm lowering my voice, sometimes students get a little confused because we want to take the coefficients, see the big 3 and the big 2, we somehow want to try to put that into the formula. And that's not it at all. That's not in calculating that's in calculating getting the answer, but that is not in calculating the molar masses. So I want to make sure that wasn't what Mike was talking about. All right. So molar masses, we just look at the formula of the compound. So here we go. I've done these, so I bet let me talk you through them. To get to the moles of the N2, we take the mass of the N2, 72.0 grams of N2. We use the flipped version of the molar mass, 1 mole of N2 over 28.02 grams of N2, and that should do it. Rounded to 3 significant figures, we get 2.57 moles of N2. We do a similar thing with our other reactant H2, 22.0 grams H2 over 1. We use the flipped version of the molar mass of H2, 1 mole of H2 over 2.016 grams of H2. The grams of H2 will cancel. We left with units of moles of H2, round to 3 sig figs. You're looking at 10.9 moles of H2. Now, if you wanted to, and you were in a doodling sort of mood, and you had enough room at the top there, actually, where we had grams before, we could go ahead and put these moles kind of underneath that. Wouldn't that be kind of pretty? So we're going to use those then to get our halve ratio. So here we go. Looks like I'm going for my halve ratio first. So halve ratios has to be in moles, can't be in grams. Maybe I shouldn't have even said that, but it's got to be in moles. And we came up with 10.9 moles of H2 divided by 2.57 moles of N2. That was halve from our grams. If you divide that out, you'll get the relative moles of H2 to N2. My builds are backwards. Every semester is a little different. So you can see now I've got the need ratio. The need ratio comes from the balanced equation. Looks like 3 to 1 to me. 3 to 1, you see where that came from? The coefficients, 3 moles of H2 to 1 mole of N2. Cool. Now I must, can't remember what my build is. I bet I go ahead and divide this out. Okay. On your calculator, if you take 10.9 divided by 2.57, you're going to get 3 sig figs, 4.24. Okay, so again, and there's a lot of things in science where I don't memorize things, I just have to concentrate when it comes time, critical time. So we need 3, and we have 4.24. Therefore, it looks like we have more than we need. Have you guys ever seen this symbol? It's like 3 triangles. It's a triangle with 3 dots. That actually means therefore. Therefore, okay, so we have more than we need. Therefore, does it look like H2 is in excess? Does that make sense? Because that was like the labels of my ratios. That's it.
Are you saying because we need 3, but we've got 4.24 of the moles,
We
right?
need 3 and we have 4.24.
Okay.
But don't we need 2 molecules of the NH3, right? That's what it's-
That's the product.
Okay.
And for this sort of calculation, we don't look at the product at all. We're all about the reactants.
Okay.
We're all about the ingredients and what our cupboard has and what we're going to run out of first. Yep. Yep. So the limited supply reactant is the N2. So don't lose track of the tree through the forest. Okay. So actually, he's our special guy. The N2, the moles of N2, grams of N2, however you want to do it. That's how we're going to answer the other 2 questions. Okay. Okay, so that was the first question. So H2 is in excess, N2 is in limited supply. The second question is, what will the mass of the excess reactant, which is H2, what will it be after the reaction has gone to completion? So kind of like we did before, we have to come up with how much is going to be reacted, how much of that excess reactant will react with a limited supply reactant. So you can see this little trick here. It's not a really trick. But instead of going back to grams of N2, I'm just going to piggyback on moles of N2. Okay? Moles of N2 over 1. And then I'm ready for my stoichiometric ratio, okay, which is going to look like, and down here's the balanced equation. It's going to look what? 1 mole of N2 in the bottom over 3 moles of H2? I think so too. 3 moles H2 over 1 mole of N2. Units of moles of N2 cancel. We have moles of H2. But in order to answer this question, do you see how we need grams of H2? So we can use H2's molar mass again. So that was that 2.016 grams of H2 over 1 mole of H2. So now moles of H2, units of moles of H2 cancel. And we have units of grams of H2. Looking like we want, what, 3 significant figures? And then that's going to be the mass that we subtract from what we started with. 15.5 grams of H2 will react with our limited supply N2. So we're close. You're like, we're not there yet? So all we got to do is a subtraction now. We take what we started with, 22.0 grams, and from that we subtract what we now know will react with the limited reactant, 15.5 grams. Now, if you get to this point in your problem and you come up with a negative number, that means that you chose incorrectly, that basically, yeah, you have the wrong limited supply reactant. So rounding it to 1 decimal, it looks like 6.5 grams of H2. That's the answer to the second question. Whew. And the third question is a little more straightforward than this. Third said, this might go back to, what's that? No, this might have been kind of like what Mike was after. So how much NH3 will be produced? Well, it depends upon what was in limited supply, which is the N2. So I think I'm going to go with moles again, so kind of make it, kind of remove 1 step. So if we just start with the moles of the limited supply reactant, which is 2.57 moles of N2 over 1. Now we're ready to go to moles of NH3, where it's kind of looking like 2 moles of NH3 divided by 1 mole of N2. So that came from the stoichiometric coefficients. So now we have moles of now we have moles of NH3, but we need grams of NH3. We can do that with the molar mass of NH3 you had on a few slides ago, which I don't have committed to memory. Molar mass of NH3 is 17.03 grams of NH3 over 1 mole of NH3. So now units of moles of NH3 cancel. We're left with grams of product. Looking like 3 significant figures? I'm thinking so. So I got 87.5 grams of product will be produced.
So we'll know that there'd be 2 moles of it because there's 2 molecules and it shows transferred from molecules to moles, right?
We did that Friday, yes, sir.
Yeah, I'm just.
Yeah. We scaled it up because mole is just 6.022 times 10 to the 23rd, so you can do that.
Cool.
Yep, I think so. That's it. That's it. So here's your other 2 ways. Okay, you're like, I don't want to see 2 more ways. Actually, a lot of students like these other ways. Maybe they've learned them or they just prefer them. And so this one, let's see. This one basically, I had to read it a few times to say what I was actually saying. So I'm going to put this R1 for reactant 1 plus R2 for reactant 2 goes to form P, some product. So basically, you have these 2 masses, and you're like, what am I going to run out of first? Well, you can take one mass and go ahead and do a stoichiometric calculation. I'll put question mark grams. Okay, so the point is that if you find out that you need more grams, how does that work? Yeah, if you need more grams than you have, then this is limited supply, okay? And if you have more grams than you need, then this is excess. Yeah, good. I can see you like that. Okay. The other one does this where, and this is kind of fun, it's just a little more work, I think. Basically, you do a stoichiometric calculation to see how much product you get from the first reactant, and then you do another stoichiometric calculation to see how much product you get with the second of the reactant. And this one makes sense to me. This one was like, oh, if I wasn't want to think too hard, I might would do this. So bottom line, whichever gives you more product is in excess. Whichever gives you least amount of product is in limited supply. So you definitely could do that too. And I've seen students probably do this one more than the other one. Okay, so this is the second one that I showed you, where you're saying, I don't know which one I'm going to run out of. Well, let's see how much product they'll both create. All right. Well, you knew it was coming. How's that go? If I knew you were coming, I'd have baked a cake. Baked a cake. And brownies. Okay. So we'll take a look at these now. Look, I have some important notes up here. So you're not doing 65 and 66, skipping those. But I added one more. Notice I added 69. So there are 3 problems instead of 4. Psych. So we'll take a look at what those look like right quick. That's got to be something my dad used to sing. If I known you were coming, I'd have baked a cake. Okay, so don't let the whole moles instead of gram things throw you off. Actually, this is like kind of a baby step, kind of a baby problem. Basically, it says the half moles I have up here in blue. I kind of wrote them underneath the 2 reactants, NH3 and O2. Bottom line is how many moles of one of the 2 products are we going to produce? Well, you're going to have to show me which one, NH3 or O2, which one are you going to run out of first? Finally, some stoichiometry that's not entirely boring. We have a 4 and a 5 stoichiometric coefficient in front of our 2 reactants. Is that not fun or what? So the 4 and the 5 represent our need amounts. So doing it the way I told you to do it, well, maybe, I can't remember my hints are. Yeah, I just hear in orange say, I would compare the need ratio in blue, or sorry, the need ratio in green from the stoichiometric coefficients to the have ratio in blue, and make a statement. Or one of those other 2 alternate ways. And then only after that can I proceed to answer the question. Oh, you clearly just, identify which is which. No guessing. No making Mrs. Snipes try to guess. Okay? Once you've identified your limited reactant, then you can answer the question. The question mark under NO, okay, how much NO will be produced? Well, You gotta do the thing on the front end first. What is your limited reactant? And then use that as your first term and go on to, now notice you don't have to take it to grams, so this is nice. You can just go leave it at moles. Well, they go up from there. Okay. Oh, this one might be one you want to take a picture of. I remember I'm going to push these out PDF under, I will definitely after class push them out. But some semesters I haven't told my students what the unbalanced equation is for these next two. And then I get home and I'm like, drat, what? Yeah, because I think Petrucci thinks by this time, I don't know if this must be Unit 4, or not Unit 4, but Chapter 4. Petrucci assumes that you can take those words and convert them to that. And not yet. So you do need to balance it first. Okay.
Get that program out that you told us about.
That's true. You can use that
Which I
program
forgot about that
online.
until just now.
Yep, use that program online. So I went ahead, like I did before, the red is actually the have amounts given in the problem. And it's kind of similar to the last one we did. After you balance it, okay, then you're going to go ahead for whatever method you want to use, come up with which are you going to run out of first, the calcium hydride or the water. Okay. And that's step 2, like a broken record. Show your rationale for identifying the one that's in limited supply. Okay, and then you're in ordinary stoichiometric calculation. Whatever is your limited supply reactant, that's going to be your first term, bada boom. Actually, it's just one simple ratio to go from that reactant to moles, question mark moles of H2. See, the other reason I like doing this is I'm like, I don't have to sweat what am I after, because I already put a question mark moles there. Okay, so you're done with that one. And then this is the other one, again, the unbalanced equation. Ammonium chloride, calcium hydroxide, delta, what's that mean?
Change.
Heat. Change in, or in this case, heat. And it means both ammonia, calcium chloride, and water. So I went ahead and, this is what I would do. Now we don't have moles, we have grams. So it's kind of like that last problem we did in lecture. You've got to go to moles, okay? Isn't that kind of nice? The author went 33 grams of each. Okay. So first balance that puppy. You can do that. And then convert from grams to moles, those masses. You can do that. Show the molar mass calculations, like how you got the molar mass, and then use the molar masses. Okay. Determine which is in limited supply. Like I said, I kind of like the ratio of the need from the balanced equation and the have from the masses. And then you're ready to do a stoichiometric calculation based on your limited reactant, whether it's ammonium chloride or calcium hydroxide. You're going to go to moles of ammonia, NH3, and then you're going to go do one last term to go from moles to grams. Okay, so that, step number 4, is what we called an ordinary stoichiometric calculation, just like you guys did in the homework that's due today. It's kind of like falling out of bed at this point. Okay? What I tried to say is on your unit exam, I won't mix the two. I won't have a problem like this where you have to identify what's in limited supply and then use that. That makes it too hard for me to grade. You'll have one to identify the limited reactant, and then you'll have ordinary stoichiometric calculations where I tell you which one's in limited supply. Okay? Awesome. Well, I think that's probably enough for today. I was thinking about going on to yields. So just come Wednesday and I'll tell you which one we're going to do. I don't know what part we're going to do next.
I have a quick question. When you're talking